Hello, everyone. Thank you for coming to my talk. So as Sundran said, I won't be talking about too much data science today. I'll be taking a more of an infrastructure approach to deploying a data science environment for your team or for your group. Don't worry if you have never heard about Kubernetes or you don't know much about infrastructure. I'll take a sort of 10-foot approach. So I hope you'll get something out of it. So I'm Camilla. I write Python, Java, and Go, and I usually work across the stack. So I've worked with big data and a bit with cloud and a variety of things. At the moment, I run a platform called Spime Labs that helps nonprofits and teams deploy JupyterHub in the cloud. So yeah, I like to talk about Python, Jupyter, and coffee and cats. And I've had too much coffee this morning already, so don't offer me another one. But if you want to talk about anything else, you can find me on Twitter or just come and grab me after the talk. So before we dive in, just by a show of hands, who here has used Jupyter notebooks for, okay. So pretty much everyone. So I'm going to show a bit of a live demo, if the demo gods are in my favor today. So this is a JupyterHub that I have running on a Kubernetes cluster. So I'm just going to log in and show you what you can sort of do with a platform like this. So when you log into JupyterHub, it will give you the standard Jupyter Notebook interface, and you can bootstrap your own Jupyter user server. So this will hopefully work. Might take a few minutes to start up. Okay, something's happening. Right. So if you've used the Jupyter Notebook before, you know that you get an interface like this that allows you to create basically an interactive computing environment that can be backed up by various different languages. I think at this point, the Jupyter community has about 100 different kernels that you can use, including R for our friends in the R data science community. So basically, what you can do is you can start up a new notebook, and you can type something, execute code, do interactive graphics, and various things like that. Let's go back to the slides. Okay, so thank you to the demo gods. This did not fail. Right. So the Jupyter project was started by a PhD student called Fernando Perez when he was finishing up his degree. And it was first known as IPython. So if you were in the Python community 5 or 10 years ago, you might have heard about the IPython notebook, which was the previous incarnation of Jupyter. So it has now grown from the original IPython version to a large ecosystem that supports multiple programming languages. I mentioned R before, but I believe there's also support for Scala and various other ones. It also has a very large ecosystem of additional projects, such as JupyterHub, which allows you to deploy and manage multiple notebooks for a team, for example. Jupyter Lab, which is the next generation of browser-based interfaces for interactive computing, as well as many others. So you can find more information about the community at jupyter.org. In addition to that, Jupyter has an active open source community. There is a large team of maintainers now, various Slack channels and mailing lists, as well as a Jupyter conference that takes place in New York. I think they had the first one last year, and there will definitely be one this year. Not only is Jupyter known in the PyData community, it's also seen very wide adoption across various industries and scientific disciplines. A few years ago, I think even Nature was doing some sort of interactive scientific papers on their website, and that was powered by Jupyter notebooks. Also recently, Jupyter has become a serious contender for more proprietary solutions, such as Mathematica. So there was a blog post recently by someone whose name I've just forgotten, but he was basically comparing Mathematica to Jupyter and saying that the Jupyter ecosystem has come quite far. So it is definitely now serious competition for more commercial and proprietary-based solutions. So it'll definitely be interesting to see what happens in the coming years to the open interactive computing space. So as I mentioned before, Jupyter is great for doing data science because it can support multiple programming languages. You can export it in a wide variety of formats, share it with people because the way the Jupyter notebooks are stored is using JSON, so you can have a wide variety of ways to share it. You can also do interactive visualizations, animations, and a bunch of other things. So if you're not yet using Jupyter for your own data science needs, I definitely encourage you to take a look. So lots of people in this room are probably more than capable of installing Jupyter on their own machines and managing any kinds of installation problems. But what happens if you're running a class, like a university class for 400 people, and you have people from various backgrounds, some of who may have never used Python before or may have never had to install anything before? So you quickly get into various kinds of issues that can cause you more gray hairs than you want to. So this is something known as, that I've called installation drift. So basically people install different versions of scientific computing packages. They have different operating systems. You have some people that don't have admin privileges. You have some operating systems that don't work well with package managers, for example, and things like that. Even though package managers such as pip and the Conda distribution have made it relatively easy, it's still possible that if you're running a team or you have a class where you're teaching programming, you'll spend a lot of time debugging various kinds of compilation errors and installation errors. Also, when you have a do-it-yourself approach, so that everyone hosts a local version of a Jupyter notebook, you quickly get into problems such as it works on my machine, because maybe they have some version of SciPy or NumPy, but then when you try to share the notebook, the results are different. So basically, JupyterHub was developed as a solution to these kinds of problems. And it's meant to help you have a centralized way to deploy reproducible Jupyter notebook environments for hundreds of users. So let's look a little bit at the JupyterHub internals and see how exactly it works under the hood. So in this diagram, we have our two familiar components, the user's browser. So this is Chrome or Firefox, whatever you use to interact with your Jupyter notebook. And then we have the Jupyter notebook server. That's the actual backend that's listening to your commands, executing your code, and sending output back to your browser. So JupyterHub sits in between these two, and it listens to connections from users' browsers and then does some logic to make sure that everything works well. So what are some of the things that JupyterHub has to do in order to make this work well? So first, when a user sends a request, it has to authenticate the user to make sure that they're allowed to perform these actions. Because we're essentially allowing users to execute code on our platform, we have to be quite careful that we don't just open this up to anyone. That can lead to severe security issues and problems downstream. So authentication. Then we have to check if this user who's trying to connect is a new user. If she is a new user, then we spin up a new Jupyter Notebook server and redirect her to that server. If the user already has a running Jupyter Notebook server, like I just showed you, then we have to make sure that her requests are redirected to that server. So the way we achieve this is we actually have two components that form our JupyterHub. We have a configurable HTTP proxy, which is actually a JavaScript component that sits between the users and the internal components of JupyterHub. So the configurable proxy is made up of two HTTP servers. One of them is facing the internet and is listening to requests coming from users' browsers. The other one is facing the internal hub components and is communicating with the hub. So the hub itself is a Python process that takes care of authentication, spawning an individual user's notebook server, and then also communicating with the proxy. So what happens if we have a new user who is just connecting to the JupyterHub system is that her request will first be intercepted by the configurable HTTP proxy's public-facing component. The proxy will establish that the user has never before had a running notebook because there is no entry for her in the proxy's routing tables. So then the proxy will forward the request to the hub. The hub will check if the user is authenticated and is allowed to spin up a notebook. And then if she is allowed to spin up a notebook, the hub will communicate with the proxy's internal facing component to establish a new routing rule for the user, which means that the next time the user wants to talk to her notebook, she won't have to go through the whole process of authenticating with the hub. So that's sort of, in a nutshell, how JupyterHub works under the hood. So I was going to do another live demo, but I thought I wouldn't push my luck with the demo god. So I made a little recording that I'm hoping to show you at least a few bits of what this system looks like under the hood when it's running. So I have, that is very small. 1 second, bear with me. Going to zoom in a little bit. So I have a Kubernetes cluster running on Google Cloud that's running a very small 3-node cluster and a JupyterHub deployment. And I'm just going to show you what happens in the proxy when I, 1 second. Right. So this is, can everyone see that? No. No. Let's try to make it a little bit bigger. Can everyone see this now? In the back as well? Okay, cool. So this is our JupyterHub deployment on Kubernetes. So you can see we're calling, I'll go over this in more detail later, but for now, we're calling Kubernetes and we're asking it to tell us which components are running on our system, so the pods. So we see that we have a hub, a proxy, and then we have a few other components that basically just make sure that everything runs smoothly. So those are running now. So this is before any user has connected to our hub. So I'm going to fast forward now to the moment where I've actually connected to the hub with my browser. So 1 second, let me just go to 255. Right. So right here you can see Jupyter Camilla. So this is my notebook server that has started up, and it's running as a pod on the Kubernetes cluster. So if you let this run a bit more, I'm going to look at the proxy logs now, and I'll see if I, 1 second, let me make this better for you. So I see that basically here, I've connected to JupyterHub, and in this line, you can see the JupyterHub has authenticated me, and it's talking back to configurable HTTP proxy, and it's basically saying this user is allowed to spin up a notebook. I've just done it for her, and I've added this route, user/Camilla, so the next time I log in, the proxy will automatically redirect me to my notebook without having to go through the hub again. Okay, back to the slides. So now you've seen a little bit of how JupyterHub works under the hood. But what do we have to do in order to actually productionize this and make it safe for users, for lots of users to use? There are some challenges that we will face. So first of all, managing CPU and memory resources responsibly. We're going to have several users sending code snippets to our backend, the Jupyter server, to execute. And we don't really know what these users will do. So some of the users might be malicious and intentionally try to starve the system, for example, by launching something really CPU intensive, or it could be just accidental. So we have to find a way to limit a user's process to only use a certain amount of CPU and memory so that we can share the platform among multiple users. Second of all, we have to find a way to clean up resources that aren't used anymore. So for example, stale notebooks or files, things like that. If we're running a public JupyterHub, for example, in a platform like Quantopian, we have to be able to scale up and down our cloud computing resources on demand. For example, if there's a big class and it's starting up, you might have 500 users trying to access JupyterHub at the same time. And in cases like these, you can't really rely on manual intervention to log into your cloud provider and provision more compute for your JupyterHub service. And last but not least, you have to be able to manage security appropriately, so authentication and also securing the connections between your users' browsers and the notebook. So let's look at some recent developments in the infrastructure space that enable us to manage these challenges. So the first challenge that we had was making sure that each Jupyter server process is isolated and doesn't use more memory or compute capacity than we allocate it to. And in recent years, a development that has made this possible is containerization. So a container is a logical concept that uses operating system features to isolate processes from one another and to make sure that they don't use more compute capacity than is allocated to them. Containers as a technology are actually not very new. They originated in the late 70s and early 80s, but didn't really gain wide acceptance until 2006, when Google deployed a Linux kernel patch that allowed for process isolation, and this became known as control groups. So even at that point, people still weren't using containers very widely unless they had some kind of specialized need to do this. And this was because there wasn't really a way for you to easily package your applications as containers and then run them. So this all changed with a startup called Docker that made a platform for people to create containerized images, things that you could share between users, upload them to container repositories, download them, and then be able to run them. So containers have solved our first challenge. We can now isolate processes, we can isolate our Jupyter notebook servers, and we can also create reproducible deployment environments, which is really good. We can just package up our application, all of its dependencies, and then we can simply deploy it to our favorite cloud provider and be done with it without having to get gray hairs worrying about installations or updating our dependencies manually. So to deploy a JupyterHub, we would need to spin up a container for every user's notebook server. Depending on the number of users, this could be 100. We also need a container to run our hub and a container for our configurable HTTP proxy. So for small deployments, you might be okay just manually restarting these containers on your chosen container runtime, or having some kind of bash script to do this for you. But if you're running a large-scale production deployment, you have to prepare for the worst case. What if one of your cloud virtual machines fails? What if you need to redeploy something while you have active users? Will you be able to do some kind of load balancing if you suddenly have an influx of users? Will you be able to redirect your users to machines in an alternative failover zone, for example, if one of your data centers goes out? So these are some of the questions that you might think about before you deploy your containerized application into the cloud. And worrying about all of this manually is not usually possible, because in a situation where you would, for example, have to load balance users to another availability zone, there just simply won't be enough time or manpower for you to, let's say, manually SSH into the machines and make the required changes. So this has been a recognized problem in the industry. And what we've developed to solve this is container orchestration platforms. So different kinds of software that manage your containerized processes for you. And there are two key, features of these platforms. So first, we have to talk about clustering. This usually means that we have a collection of cloud-based virtual machines that act as a single machine from the point of view of the client application. So your JupyterHub components shouldn't really care about which exact machine they're deployed to. They should be agnostic in this sense, so the cluster essentially acts as one machine, which makes it easy for you to fail over to another cluster if you have a machine failure, let's say. The second component of the software is the actual orchestration itself. So you need some kind of component that will take care of things for you, scheduling and managing your containers, load balancing failover, restarting containers that failed, and so forth. There are several software products in the market that will help you do this, but the JupyterHub team has made a choice to go with Kubernetes, which is an open source orchestration system first developed at Google and open sourced, I think, a few years ago. So the Kubernetes community has been growing quite rapidly. A few years ago, the main Kubernetes conference, KubeCon, had a few hundred attendees, but last year in Austin, Texas, the conference had grown to 4,000 attendees. So the open source project and its adoption is definitely growing. What Kubernetes offers you is it offers you a cluster of nodes where you schedule your applications, and a master, which takes care of things such as storing the cluster state, checking on the health of the nodes, and so forth. So there are two main advantages that you have when you use Kubernetes. So in the past, in the DevOps space, we have had two philosophies of how you provision your machines to deploy applications such as JupyterHub. One of them is declarative, and the other is imperative. So in imperative modes, you basically write a little recipe of the exact steps that you need to perform in order for your machine to be ready to deploy an application such as JupyterHub. The other way to do this is declarative. So instead of writing down the steps that you need to do, you define what you want the state of the infrastructure to be. So we want our Kubernetes cluster to have 3 nodes. We want each of our applications to have 2 replicas, and so forth. But you don't define how this should be achieved. So this frees you from having to worry about how things are achieved, and instead, Kubernetes can work for you to continuously make sure that the reality of the cluster and its health reflects the state that you want it to be. Additionally, Kubernetes allows us to abstract infrastructure. So instead of worrying individual machines or low-level networking details, we have an abstract set of infrastructure objects, pods, services. They represent different kinds of things about how our JupyterHub should be running and how it should be deployed. This usually makes it easier for people who don't have much experience in the infrastructure space, like me, for example, to have a functional Kubernetes deployment. So the way that you would deploy a Kubernetes application is you create these kinds of YAML configuration files, and then you send post requests to a REST API that's on the Kubernetes master, and then the Kubernetes services will make sure that your application is deployed to the nodes. For smaller things, this is okay, writing YAML by hand. But for larger projects like JupyterHub, for example, where you have several components that need to communicate with each other, this can get quite tedious. And also, you won't be able to, for example, roll back or upgrade very easily because you'll have multiple configuration files that need to be changed simultaneously. So to make this easier, the Kubernetes community has developed something called Helm. It's a package manager for Kubernetes that exists on the client. So it exists both on the client, so on the shell terminal that you're using to communicate with your cluster. And there is also a component on the cluster itself called Tiller that receives these commands and then makes sure that your application state reflects what you want it to be. So Helm basically allows you to share Kubernetes deployments as Helm charts, and it also makes it easy for you to upgrade or roll back applications. So the good news is that the Jupyter team has already produced a good Helm chart for us to use. So if you are trying to deploy JupyterHub, for example, in your own cloud infrastructure, you don't have to worry too much about writing these yourself. Right. So to prepare for this talk, I tested out the open source JupyterHub Helm charts on 3 different commercial cloud providers. Google Cloud's Kubernetes engine. Amazon, unfortunately, doesn't have a native Kubernetes solution yet. They've recently launched something called EKS, but it was still in preview mode only, so I wasn't able to run tests with that. If you're more of a do-it-yourself kind of person, there are 2 approaches to deploying Kubernetes and JupyterHub on Amazon. So you can use a Heptio CloudFormation template that will deploy all the components for you, or you can use a command line tool called kops. Both of these do require a bit of extra effort to set up things properly, and also extra effort to manage the deployment. Last but not least, there is Microsoft's Azure Container Service, which is also still in preview, but it's already public, so you can try it out. So Google Kubernetes Engine is definitely the easiest of these to work with. Things pretty much work out of the box. You download the Helm chart from JupyterHub's open source repository, and then you run a few commands using Google's native shell tool, and things work without any hiccups. The other good part about this is that you don't actually have to manage any part of Kubernetes yourself. The Google Kubernetes engine comes free of charge, and the only thing you pay for is the actual compute instances that make up your node. So I did some pricing comparisons, and if you want to run a small demo of JupyterHub with 3 nodes and 1 virtual CPU and a bit of RAM, if you run it 24/7 for a month, the cost will be about £70. So then the The next trial I did was Kubernetes and JupyterHub and AWS. So as mentioned before, they don't have a native Kubernetes solution, which definitely makes it a lot harder to get a fully functional deployment. I didn't try out Heptio's CloudFormation template, but I did make a cluster with kops. This does require quite a lot of knowledge about configuring DNS servers, for example, so that the internal Kubernetes components can talk to each other. And this will also be more expensive for you in the long run because you have to manage the machines that run the Kubernetes infrastructure itself. Whereas with Google Cloud's solution, you get that sort of for free. You just pay for the nodes that actually will run your JupyterHub deployment. If you're interested, there is a link to a demo of deploying Helm charts and the whole JupyterHub process on a cluster created with kops. And last but not least, the Azure Container Service. So this is more similar to Google Cloud in many ways. You just have a simple command line process for deploying JupyterHub. It's relatively easy apart from a few hiccups, which is expected because they're still in preview mode. But other than that, it does work very easily. AKS is also similar to the Google Cloud Kubernetes engine in the sense that it doesn't charge you anything for the actual maintenance of the cluster, only for your compute node. Some Kubernetes features, unfortunately, are not yet available on AKS. So for example, if you want to have role-based access restrictions to your Kubernetes cluster, so you have an admin that's allowed to do some things and some other users, then that's not yet available on the Azure system. And although you can't really compare the Google Cloud and the Azure offering like one-to-one because the machine sizes that you use for your nodes are slightly different, I tried to pick out things that were as close to each other as I could. So if you run a small demo cluster with 1 core and 3.5 gigabytes of RAM, it will be about £82 per month if you run it 24/7. So usually when you make choices for deploying an application such as JupyterHub into the cloud, I usually make a little matrix of things that matter to me, and then I compare the different providers based on that. So you might want to do a similar exercise in your team if you're planning to deploy JupyterHub. So for me, the most important things are, is it easy to deploy? I don't have much in-depth knowledge of networking and infrastructure, so the tools have to work pretty much out of the box. Is it easy to deploy the application itself? So how easy is it to get JupyterHub with Helm to work? And actually, the good news is that once you've got the Kubernetes cluster set up on whatever cloud provider you need, the part that comes after that is super easy because Helm is actually cloud agnostic. So even if you want to migrate from Azure, let's say, to Google Cloud, you can keep a big chunk of your deployment infrastructure because Helm doesn't really care what's sort of underneath. So that's the good news, is that once you've got the cluster set up, the deployment part is very easy on all 3 cloud providers. And then you also have to think about the cost. So with Google Cloud and Azure, you get the Kubernetes part for free, whereas with AWS, at least until they launch EKS, you'll still have to pay for the compute instances that run the actual infrastructure itself. So to summarize, we've seen how Jupyter can make your data science experience better and how JupyterHub can make it easier for large teams to have reproducible and highly available Jupyter environments. We've looked at some JupyterHub components under the hood and how Jupyter works. And we've also looked at some of the infrastructure developments that have happened in recent years to enable us to provision these kind of highly available infrastructures in the cloud. So yeah, that's pretty much all I had, and I'll be happy to take any questions that you have now or after the talk. Do we have a mic? No, okay. I'll just repeat the question. Yes, please go ahead.
Yeah, thank you for the fantastic walkthrough. I was wondering if you looked at kind of extension of JupyterHub. Binder was mentioned earlier today because it gives you more. It basically builds on the same infrastructure but gives you more functionality. And Report Talker is a fantastic addition as well.
So the question was about whether I had looked at Binder and other extensions to JupyterHub, and the answer is no, unfortunately not yet. I've been working with vanilla JupyterHub deployment, but certainly I would be happy to take a look. Anyone else? Yes?
So I've tried to deploy things like JupyterHub on a Kubernetes cluster, but I tend to work in a private cloud environment where you want to give users access to the persistent storage they're used to running on that same environment. So unlike, say, in a GCP sort of environment where you can spit up a volume that's unique to that user, try to integrate it with an established thing. Could you sort of comment on the development in terms of how JupyterHub and the persistent storage on not the public cloud? So if you're not trying to run it on Azure or GCP, but on something else, is that being actively worked on? Because that's my pain point right now.
So are you running Kubernetes in your private cloud?
I've tried. I've set it up. These are cloud platforms which are typically sort of like pre-allocated. I don't have the ability to spin up brand new nodes. They're sort of set. They're think of them more closer to bare metal kind of things as opposed to a full Kubernetes installation.
So if you do it on Kubernetes, you can definitely have something called persistent volume claims that will sort of allocate for every user a persistent volume that is persisted even if the actual pod that's running the container dies. Now, I mean, you can strip off all of this abstraction and go down to the Docker container itself, and that obviously allows you to mount a volume that can then be persisted. So, I mean, you might have to go down there without the whole Kubernetes part, but unfortunately I can't comment exactly on how that would work.
Okay, that's good. Thank you.
What do you think about the pros and cons of services like SageMaker and whatever GCP will offer as an alternative that will also allow you to spin up notebooks? Seems like in an even more abstracted way than this versus JupyterHub plus Kubernetes?
Okay, right. So I know that there are several cloud-based providers that are doing things like JupyterHub, but as far as I know, things like Colabs and SageMaker, they're single notebook environments for a user, but I think JupyterHub is more useful, for example, when you're in a university. You have maybe some legal/IP issues where you can't use a public cloud notebook, like private data, research data, and you need your own deployment. But apart from that, I don't really have any other comments. I haven't actually used any of those publicly available Jupyter notebooks.
Hello. So I was wondering, for the small cluster that you had with 3 nodes and 1 CPU, do you have any idea of how many notebooks, so how many Docker containers you can actually run while keeping it stable?
That's a very good question, and I was going to do some performance measuring before I came here, but unfortunately I didn't have time, so that would definitely be a good extension to this talk. I've tried running about 5 or 10 containers, 5 or 10 Jupyter servers in containers, but without doing anything super intensive, actually. So I wouldn't know how they would behave. That was pretty stable, but I wouldn't know how they would behave if I tried to compute fractals in the notebook or something else that takes a crazy amount of compute.
Thank you. I have a couple of questions. First one is, the architecture or the implementation that you did will also work for Jupyter Lab, which is the next release coming. Have you looked into that?
I have not tried JupyterHub. I have not tried to deploy JupyterHub in this Jupyter Lab in this manner, so I unfortunately cannot comment on that.
But in this particular case, it would work with the other things that support that are supported by Jupyter, like Julia, for example, will be fine.
I would assume yes.
Okay.
So I have it. It's fine.
Okay.
Great. And then the big thing about a lot of this Jupyter notebook is that we share a lot of data. And one of the biggest problems is if it's somewhere in a machine somewhere, you have to move that data to that machine. Have you found a way of easily resolving that issue and also maintaining security for the data itself?
This is probably really bad to say because of GDPR and other stuff that's coming up, but no, I haven't. I haven't found a good way. I mean, Kubernetes has many add-ons and plugins that you can use to make it really secure. And whenever you deploy things like JupyterHub as a public service, you should always, for example, make sure you use SSL. And the good part about JupyterHub is that they've made it really, really easy for people who have no previous experience in configuring encryptions to spin up an SSL connection between every user and the notebook server. So there are some built-in features that definitely make it sort of secure, but for large amounts of data, I wouldn't be able to say, unfortunately.
Thank you.
Hey, let's say that I have an environment with 100 occasional users that will use a notebook maybe twice per month. Does JupyterHub somehow handle spinning up and tearing down instances as the compute power is needed or not needed anymore?
Yes, it does do that. So the question is about spinning up and basically deleting unused notebooks. And yes, there is an automatic mechanism in JupyterHub that will call notebooks once they've been inactive for a certain period of time. I can't remember off the top of my head what that is, but it's definitely configurable. So if your user closes the browser but forgets to stop the notebook server, then yeah, in a few hours, I think Kubernetes or JupyterHub will tear it down. And the Kubernetes cluster itself can scale up and down depending on your needs. So you can set up auto-scaling, so it can go up to 6 nodes, for example, if that's what you need, and then Jupyter will sort of manage that for you. But it will definitely clean up stuff that's not used.
Any other question? No. Well, thank you.
Thank you.